Hi, I'm Ta-Wei, and I'm going to talk about maximum flow by augmenting path in N to 2+o one time. This is joint work with Aaron Bernstein, Joakim Blikstad, and Thatchaphol Saranurak. So for the maximum flow problem, you are given a directed graph G with n vertices and m edges, and you also have capacity on the edges and one source vertex S and a source vertex T. And the goal is to compute a flow that route as much demand from the source to the sink as possible while obeying the capacity constraint, that is, the flow pattern through each edge cannot exceed the capacity of it. And for each intermediate vertex, the incoming flow of it should equal to the outgoing flow of it. And equivalently, if you split each capacity edges into like multiple copies, then the problem is the same as finding the maximum collection of edge disjoint paths from the source to the sink. So for example, here we have a graph. Throughout this talk, for simplicity, I'll always assume the graph to be unicapacitated. And in this case, there is a flow of vector 3, as sends 3 units of flow to T. Each edge is used at most once, and each vertex receives and sends out the same amount of flow. However, this is not the maximum flow. The maximum flow on this graph will have phatic 4 as shown here. So to solve this problem, a classical combinatorial approach is to use something called an augmenting path. Say we start with the input graph and we find an ST path in this graph. So this will be what we call an augmenting path. We can send one unit of flow through this path to augment our current flow solution by one. And after that, we will reverse all the edges on this graph and consider its residual graph. And in the residual graph, we'll keep finding augmenting paths. So say we find these two augmenting paths, and then we send one unit flow through each of them. And then we will reverse again the edges on it and then create a new residual graph. Now, crucially, even though there's no ST path in the original graph that does not intersect with our previous flow paths, because we are considering the residual graph, there's one more such path that crucially use this purple edge. So by using this purple edge and sending a unit of flow through it, we're effectively canceling out the flow that we sent in the opposite direction in previous iteration. And it can be proven that by continually doing this until there's no ST path, you'll end up with a maximum flow. So this concept was first introduced by Ford and Ferguson, and subsequently, there have been a lot of improvements on finding a single operating path faster or finding multiple ones at the same time. And at the end, we have this Goldberg and Rouse algorithm, which runs in time n to the 3/2 or n times n to the 2/3. So this was the best combinatorial algorithm for max flow. After Goldberg, Rouse, and algorithm, people sort of get stuck with this combinatorial approach. So there comes another line of algorithm based on continuous optimization. So the overall idea is to apply optimization methods such as the IPM on the maximum flow or min cost flow linear program. And by doing so, it will reduce solving the linear program to solving a sequence of subproblems on the graph. And people came up with fast algorithms to solve these subproblems and even do it in sublinear time using dynamic graph data structures. Deitch and Spielman was the first one to use this continuous approach for maximum flow. They got a running time of m to the 3/2. And after that, there has been a lot of exciting works on this, and ultimately it culminated into the recent breakthrough by Chang, King, Liu, Peng, Probst, and Sachdeva, who gave an almost linear time algorithm for maximum flow and min cost flow. So these almost optimally settle the time complexity for maximum flow. So one may ask, why are we still studying combinatorial algorithm? So there may be a few points one can make to favor combinatorial algorithm against continuous one. So for instance, you can argue that the continuous combinatorial algorithm make progress more intuitively. You just follow flow paths, sense flow through them, and then take the residual graph and keep doing this. But for continuous optimization methods, such an intuition is sometimes less obvious because the IPM usually updates the flow in like a fractional manner. And the combinatorial algorithm often use simpler machinery, so push label and blocking flow are all pretty elementary uh, things, whereas the continuous optimization methods, um, all the current such algorithms sort of use heavier machinery, and they need to use dynamic graph data structure to really speed up the algorithm. But you can also argue that there is where they gain the speed up. Um, you can also say that combinatorial algorithms are sometimes more implementable. Like some of the previous combinatorial algorithms are actually used and work well in practice, but the same thing is less clear for continuous-based method as of now. I guess none of these are like inherent to whether an algorithm is combinatorial or continuous. At least we don't even have a good definition of what that actually means. So it's not really about like favoring one type of algorithm over the other. Instead, I think it is just given how fundamental the maximum flow problem is, it's very natural to want to see whether there are different approaches that get like slightly faster or like even the almost optimal running time for such a fundamental problem. And by doing so, techniques for solving one problem um, have a chance to be transferred to solving another problem. So for example, another fundamental problem would be the maximum matching problem. On bipartite graph, we have an M-Ruden algorithm by Hopcroft and Cart, but every subsequent improvement after that was based on continuous optimization methods. So you reduce it to maximum and use the continuous machinery to get faster running time. So for bipartite matching, we have this almost linear time algorithm by the almost linear time flow algorithm. But for the general matching problem, even though we also have the similar M-Ruden time algorithm, because the size of its linear program has exponentially many constraints, um, people don't know yet how to apply all the continuous machinery that we have to speed up these problems. So for example, by studying combinatorial algorithms for a related problem on maximum flow, hopefully we can transfer some techniques and ideas to the number pattern matching problem and get a faster running time. So in this paper, we study combinatorial algorithms for max flow. We get a faster running time of n to 2 plus 1. And this improves on uh, the m, the m to the 3/2 algorithm by Gober and Rouse. And even for the unit capacity graph, this bound was known in the 70s, but we are also the first one to improve it by a combinatorial algorithm. And the running time of n2 2 plus 1 is almost linear in dense graph. So at least in this region, we matches the almost linear type flow algorithm. And it's worth mentioning that there is a very recent independent work by Chicho and Kana, who gave a combinatorial algorithm for bipartite matching that also had the same running type of n squared plus little o1. And as I say, one hope we have is that by getting a faster combinatorial algorithm for Maxwell, maybe we can solve non-bipartite matching faster as well. And we also hope that at least some of the ideas here may lead to even faster and much simpler Maxwell algorithm, which could be potentially implementable and practically fast. So now let me give an outline of how algorithm works. So one thing to note that is in directed graph, you actually only need to solve maximum flow very crudely. And if you have such a crude approximation, you can just compute it and take the residual graph and then repeat. And this will converge in very few iterations. So this is what our algorithm components will be focusing on. So our algorithm has three main components. So the first one is the weighted variant of the classic push label algorithm. It is additionally given some sort of a hint, and when the hint is good, it will be able to find flow faster than the unweighted algorithm. And to compute such a good hint, we prove a structural theorem which says that if you have something called a directed expanded hierarchy of the input graph, then this naturally induces like a good hint that can speed up the flow computation. And to actually compute the expanded hierarchy, we use some bootstrapping. So internally, it solves some flow problem, starting from easier one to harder one. So the very first flow problems will be very easy, so we can just use unweighted push label. But as the problems get harder and harder, we'll need like more and more powerful flow algorithm. But luckily, because we have the lower level of the hierarchy will give us a better and better wave function. Our weighted push label algorithm will become better and better and are able to solve this harder and harder flow problem. And ultimately, in the few iterations, we'll be able to construct the full hierarchy that give us a way to solve the original flow problem that we wanted to solve. So in this talk, I'll be focusing on the first two components of our algorithm. These two components are relatively simple. The weighted push label is just a simple modification to the classic push label algorithm, and the intuition why directed expander hierarchy works is also conceptually quite simple. However, our overall algorithm is still quite involved due to the need to actually construct this expander hierarchy. So a lot of details go into how to make things actually work there. And for the sake of time, I won't have time to go into it. But we hope that if we have like future development and more understanding of expander hierarchy, this part can be significantly simplified and we will get like an overall like quite simple algorithm. Okay, so now I'm going to give a review on the standard push label algorithm. So in the algorithm, you'll have a parameter h, and you also assign labels to each vertex between 0 and h. You think of the label to be equal to the distance from vertex D to the sink in the residual graph, and you think of the height as being roughly n. So let us label the vertex by its distance. Now we define an edge to be admissible if it is go forwards in the distance level. And we are only allowed in the push label algorithm to send flow through an admissible edge. So we only consider augmenting paths that consist solely of admissible edges. Say we find such an augmenting path, we send a unit of flow through them. Now we reverse it to make the new residual graph. And then we need to maintain the label so that it still corresponds to distance. One thing to notice here is that the distance in the residual graph to the sink only increase throughout iterations. So what we can do is that for each vertex to be relabeled, we check all its out edge and see if there's still an admissible edge pointing to a lower level. And if there is, the vertex can stay where it was. Otherwise, we have to increase its level by 1 and check again. And then after all the relabel is done, we can find a new augmenting path through potentially new admissible edges. So to analyze the running time, we can see that each vertex at each level, we'll need to spend like its degree time to check for like new admissible edges and new push operations available. So over this for a single level, it takes OM time. And so this amounts for the final NM algorithm. So to speed up the MN running time, we notice that the bottleneck is having to check the degree, like all the out edges for every vertex whenever it's relabeled. And to speed it up, we need to somehow be able to check fewer edges than this. So the idea is that one can notice not all edges in the graph are equally frequent or important for finding approximate flow. And so, for instance, some of the edges might be very crucial. You need to use them a lot to find a good approximation. And for other edges, maybe there are like a lot of ways to reroute flow around it so that you don't really need to use such an edge that much. So to model this, we assign an edge weight to an edge weight function. And then instead of considering an arbitrary flow path, we only look for flow paths that are very short with respect to this weight function. And what this results in is the effect that edges with higher edge weights will appear less frequently on flow paths than edges with lower edge weights. And we will try to exploit this fact and only check longer edges less frequently. So concretely how this works, we again consider the same graph, but now with weights on the edges. And instead of setting the label to be the distance, unweighted distance to the sink, we'll set it to the weighted distance. And an edge is said to be admissible if it's tied across distance level. So if the difference between the labels of its two endpoints is equal to its weight. And again, we only consider pushing flow through an admissible edge. So this alone will not give us the chance to do the speed up that we want. Instead, we will need to relax the equality conditions here a little bit. So for example, instead of saying an edge is admissible if it is exactly tied across distance level, we will say that it is tied if the difference between LU and LV lie between the range of say WE and 2WE. And this creates like a gap of WE here, which will allow us to argue that we don't need to recheck each edge every time a vertex is relabeled. And because an edge with weight W will not change from not admissible to admissible very fast and vice versa. You will only change it like every WE iteration. So we'll only need to check it that many iterations at a time. So to do a quick analysis, each edge will be checked and pushed only n over WE times instead of n times. And the reliable time is the same. So overall, this gives an n squared plus n times the sum of inverses of the weights time algorithm. So when a lot of the weights are large, this can be much faster than n times n. And crucially, for correctness, we prove the following lemma, which says that the flow that our push label finds will be approximate against the optimal flow restricted to short paths. And what this means is that if you combine these two conditions, you can see that if we want an efficient algorithm that can produce a good approximate flow, we need the wave function that we started with to satisfy the following two conditions. So the first condition say that there must exist some approximate flow such that each short path is short has weight roughly n with respect to our wave function. And this by our lemma will ensure that the push label algorithm will find a good approximate flow. And for efficiency, we will need the sum of the inverse of the weights to also be roughly n. So plugging in this back to our running time analysis, this will give an n squared algorithm. And so this will be our goal to construct such a good wave function. So to see how a wave function might look like, we can consider two extremes. So on the left, we have a DAG, which is like a graph without a cycle. So this is like the least connected kind of directed graph. And we know that for this type of graph, there is a topological order on the vertices such that each edge only points forward in the topological ordering. And in this case, we can set the weights to be the difference of the topological order of the two endpoints. And to verify that this is good, we can check the two conditions. For the first conditions, it's not hard to see that like not just the maximum flow, like in fact, all the paths in this DAG must have weights at most n because it can only go forward in the topological order as it goes. And for the sum of inverse, you can do a simple calculation to show that this will be bounded by n times the harmonic sum, which is n log n. So both of the conditions are satisfied. We have a very good wave function for DAG. And the other extreme will be like a super well-connected graph, a complete graph. So in this graph, intuitively, because it's so well-connected, every edge in this graph is not very important to find for finding an approximate flow because there are so many ways to reroute flow around it. So in this case, we will just set the weight to be the number of vertex. So this is very large. However, we can still see that it's not hard to see that there exists actually a maximum flow in a complete graph that has such that each flow path has weight at most 2n. And you can check that the sum of the inverses of the edge weights is also bounded by n squared, which is the number of edges, times 1 over n, which is again very small. So in both extremes, we have a very good wave function. So now the question is how we can combine the ideas from both of them to form a wave function in general. To do that, we'll need to relax the complete graph condition slightly. We'll consider something called an expander. So a graph is a phi expander. If you look at every cut, there are a large fraction. There are for each cut, the edge crossing this cut is at least a 5 fraction of the volume of the cut, where the volume of the cut is the sum of the degrees of the vertices in the cut. So this, like, the volume is like a natural upper bound of how many edges can be incident to the cut. So a graph being a phi expander says that actually a decent fraction of those edges actually cross the cut. So you think of phi as being relatively large. So the key property of expander that we're going to exploit is that expander is like a very good router for flow. If you put any reasonable demand on the expander, it can be routed very efficiently with short path and low congestion. So what this means is that expanders in the flow sense are very similar to complete graph. They route things very efficiently, and we can afford to set its weight to be very large. And it's not hard to verify that for expander, this is indeed a good wave function. And what is good about expander is that compared to using complete graph, is that expander allows us to do something called expander decomposition. So expander decomposition says that for any graph, for any directed graph, you can write it into 3 parts. So the first part will be expanders, and the second part will be a lot of edges connecting them that form a DAG. And there may be some leftover edges, but we can show that there are only very few of them that we call back edges that can go backward in the topological order of the DAG. So another way to see it is that if you, for an expanded decomposition, you can remove very few back edges so that the resulting graph, in the resulting graph, every strongly connected component is an expander. So let's say we are in the case where there are no back edges, so we just have a bunch of expander connected by a DAG. Then a good wave function in this case is very natural. We just for each edge there that is in some expander, we just set its weight to be the size of the expander that is in. And we now pick like a good topological order. I'm not gonna define what good means, but we pick such good topological order, and then we just set the weight of the dagger is to be the difference between the topological order of the endpoints. And to get an intuition why this is a good wave function, we can consider rerouting the maximum flow so that it becomes short with respect to our weight function. So we just simply reroute it within an expander so that you use very few expander edges. And because the size of the expander is sum up to n, the total contribution of expander edge on each flow path is bounded by roughly n over 5. And again, for DAG edge, you can only move forward, so the contribution of DAG is another factor of n. So overall, this shows that there is a good flow that is short with respect to our natural wave function for this case. And it's also not hard to do a simple calculation to show that the sum inverse of the weights in this case is also very small. So in this expander plus DAG case, we have a good wave function by combining what we know from the two extremes before. So to go beyond that, a natural idea is to just, when there are back edges, we do, again, an expander decomposition with respect to these back edges. And to do that, we need to generalize the notion of expander a bit. We now say a graph is expander with respect to some terminal edge set F. If you look at every cut, the edges crossing the cut is at least 5 fraction of the volume of the cut induced by the terminal. Now, the volume of the cut induced by F is just, you count the degrees, but you only count degrees that correspond to edges in F. A similar property for such an expander can be shown. If we have an expander with respect to F, you can route any reasonable demand on the terminal edges to be short and with low congestion. But notice that now short means that it has very few terminal edges on the path, but we have no guarantee on the number of non-terminal edges. So ideally, what this gives us is that if we do, so we say we do the first expander decomposition, we get some packages, and now we do another expander decomposition with respect to these packages. And because the volume now is smaller than before, the expander that we get will be larger, and it will be like a laminar, will form a laminar structure. It will contain some of the lower level expanders, And then there are still some remaining packages. So we do another round of expanded decomposition. And hopefully at the end, we'll get some hierarchical structure that form this nice laminar family of expanders. And underlying them, this is a deck that connecting everything. So pictorially, this will be on a high level what a directly expanded decomposition that we use in this paper look like. And even though I didn't give you a precise definition, hopefully you see how it should look like structurally. So we can analyze the expanded hierarchy. So what should we put on the weights? We will just use, again, a very natural wave function that we call W sub h, where h is the expanded hierarchy. So for an edge that is ever an expanded edge in some in some expander in some level, we just set its weight to be the number of vertices in the expander. And again, for the deck, we'll pick like a good enough topological order that respects the expanded hierarchy. I'm not gonna define what this means again, but there is some easily computable topological order that you can pick, and then just set the weights of the edges to be the difference of the order between the endpoints. So now we want to argue that there's still like we can reroute any flow so that it becomes short with respect to this wave function. How we do that is very simple. We start with the flow, and then we just go from the top level of the hierarchy to the bottom level of the hierarchy. And we consider for each level, we consider the expander that it is in. Say it is with respect to some terminal edge set F. And then we just use its property to reroute the current flow so that it becomes short with respect to F. So that each flow path now contains very few edges in F. And now you can see that because the edges in F have weight C, and the size of the expander in each level sum up to N, and plus that there are only very few levels in the hierarchy, you can see that the contribution of the expander hierarchy for our resulting flow at the end will only be, again, roughly N over 5, which is small. And for the deck edges, because we pick like this good and respecting topological order, we will be able to show that this part can be charged to the expander edges. So this part is also negligible. So I've shown how you can reroute the flow so that it becomes short, but I haven't argued that the resulting flow will be like good enough. So like the congestion doesn't blow out. We still have a good approximation. But in fact, this can be done, but like not with this exact rerouting argument. We need like in the real version, we need like a more sophisticated version that will handle the congestion blowout. But overall, we can indeed show that for any flow, you can reroute it inside the expanded hierarchy so that it becomes short with respect to our weight WH, and it still has approximately the same size. So this shows that the natural wave function induced by the expanded hierarchy is indeed good and can be used to speed up our weighted push label algorithm. Okay, so to recap, I've very briefly go through the two components in our algorithm, the weighted push label and directly expanded hierarchy. Hopefully now I've convinced you, at least intuitively, that if somehow magically you're given the directly expanded hierarchy, you can find a good wave function from it and use it to solve max flow efficiently and approximately, and then you will recurse on the residual graph to get an exact max flow. To say a few words on what goes into this constructing expander hierarchy part. So the main difficulty lies in the fact that we're not, when doing expander decomposition with respect to the terminal, we're not going to always be lucky and get an expander that form a laminar structure containing lower level expander. So there might be some non-nestiness happening in the meantime, which we don't know how to analyze. So we need to spend more work in this to try to fix this non-nestiness to force that everything in the end will form like a nice and hierarchical and laminar structure that you've seen in previous slides. So this is what goes into the algorithm for constructing expanded hierarchy mainly, and the only complication in our paper. Okay, so this is all I got. Feel free to check our archive for more detail, and thank you for listening.